So here is just a small in-body integration where I'm throwing an interloping star at a binary. And you'll see that during these mini passages where the three stars enter this sort of chaotic scrum, what we call the resonant part of the encounter, that I'm going to change both the components of the binary and the orbital properties of the binary it produces. And even though this is a formally chaotic process, there are two sort of key features that come out of this. The first, and this is due to a monumental paper by Douglas Heggie in 1975, is that hard binaries, that is, binaries with binding energy that is greater than the average kinetic energy of stars in the cluster, will typically harden in these encounters. The hard binaries get harder, the soft binaries get softer. And so what that means is that on average, the binaries that I hit with other stars and black holes are going to shrink their orbits, get kicked out into the halo of the cluster, dynamical friction brings them back in, and this process continues again and again until either the binary is ejected from the cluster, it merges in the cluster, or the cluster is torn apart by galactic tidal fields around it. All right, so that is my quick introduction to binaries in star clusters. But what I actually promised to talk about today was, can we connect this to what we understand about cosmology, right? Can we connect this to the sort of state-of-the-art simulations that we spent all of yesterday learning about, right? Because we're now getting to the point where our galaxy zoom-in simulations, right, can resolve individual giant molecular clouds, right? They're getting small enough spatial and mass resolution where they can see infalling gas clumps, right? And so what I want to ask, and that's kind of the point of this talk, is can we connect our sort of state-of-the-art in these galaxy simulations to what we want to know about the population of merging binary black holes and detached black hole main sequence stars that we see. Right? And so that led us to a project that was started, I think, right when I was moving from MIT to the ITC, which we ended up calling Great Balls of Fire. Fire is the simulations that Dusan and others were talking about yesterday. I can't take credit for this title. That was entirely Mike Grudich, but we all loved it the second he said it out loud. And the basic idea of it is that we want to daisy chain our state-of-the-art numerical simulations, going all the way from our Milky Way mass simulations of galaxies to high-resolution zoom-in simulations of cloud collapse and star formation, all the way to in-body simulations of star clusters that we evolve forward to z equals 0 with all of the information that we can extract from these cosmological simulations. So our first three papers on this have either been published in MinRAS or come out on the archive. To get into a little bit more detail about this, we started off with one of these fire simulations, in particular the M12I fire simulation, which represents, at least from the Fire 2 suite of simulations, the closest that they were able to get to a Milky Way mass simulation. The nice thing about this is that it has relatively small particle masses, about 7,000 solar masses. It can spatially resolve structures down to about a parsec, and it can resolve the phase structure in the ISM itself, which means you have all the ingredients you need to look into the formation of giant molecular clouds in these simulations. And members of the FIRE collaboration, in particular Dave Guzhinov and others, have done a lot of work extracting the giant molecular clouds that are formed in these simulations. And so using the techniques that he developed, this algorithm called the Cloud Finder, we went back through one of these simulations, the M12I, and extracted all the giant molecular clouds that formed over its z of 100 to z equals 0 time history, right? So using this cutoff in the virial ratio, taking into account the thermal and magnetic energy in here versus the gravitational energy, we extracted all of the nearly 100,000 GMCs that formed in this simulation. We then used a series of high-resolution, ultra-high-resolution cloud collapse simulations from Mike Grudich to map those GMCs and their properties onto star cluster initial conditions, right? So these were very high-resolution simulations done using the same feedback physics as the Fire galaxy, so there's consistency there. And then we map, using this grid of simulations, the GMCs from the galaxy onto the initial t equals 0 conditions for star clusters. Finally, we picked a single particle from those GMCs itself, used that as an effective tracer particle for each of the clusters, and extracted the tidal field that it experienced from the galaxy. So we went through, extracted the tidal tensor of the gravitational potential along the way. which gave us all of the information we needed to start realistic in-body star simulations of star clusters with star-by-star resolution. Right? I can talk more about those if people are interested, but I'm going to instead skip straight to sort of the results at the end. And so essentially what we're doing, right, is a zoom in of a zoom in. Right? So we have this Milky Way-like galaxy. It forms all of these star clusters in it. The red star clusters are young star clusters. The blue star clusters are globular cluster-like things that were formed in the main galaxy. And the teal clusters are actually those that were formed in dwarf galaxies and then accreted later on during the history. And so if we zoom in on these with pseudo-HST observations, these are HST pseudo-observations of the z equals 0 state of each cluster, right? So we're transferring each star into what its actual PSF would look like in Hubble. And so essentially we're going all the way from 10 kiloparsec scales to parsec scales with individual stellar masses. If we look at, as an example, what the masses of these clusters look like over time, you see the normal dip that you would expect due to stellar evolution mass loss and tidal stripping, but you also see these weird dips in here. And each of those are encounters with various structures in the original fire galaxy. So either encounters with other GMCs, disk crossings, things that essentially strip almost instantaneously large numbers of stars from the outer parts of the cluster. And if we put all of the binary black holes, as an initial example, on a plot here, this is looking at both the M12I galaxy and a few other dwarf galaxies that we threw into the mix, we can replicate this nice tail of things in primary mass going from about 40 solar masses up to 200 solar masses. Right? So right off the bat, we can already explain from this population, these initial conditions, the things that LIGO is seeing. But how did we explain these things? Right? So if I want to fill the mass gap, there's really two different ways I can do this. The first is I either merge black holes hierarchically into it. Those of you that have seen me give talks before have heard me talk raving about this for 5 years. Or we can change the mass gap, either by changing stellar evolution or by changing the input stars themselves. I'm going to start briefly by talking about hierarchical assembly. So the idea is pretty straightforward, right? I start off with two stars that are born from stellar collapse. If they merge inside the cluster, they are going to produce a new black hole with a unique mass and dimensionless spin. And that black hole, as long as it's in a cluster environment, can potentially exchange into another binary and merge again, right? And so I can continue this process in theory indefinitely, but in practice, I am limited by the recoil kick that every black hole gets during merger. Now, for non-spinning equal mass black holes, that recoil kick is non-existent. But as I crank up the spin, which happens during these mergers, suddenly I get substantial recoil kicks due to conservation of momentum from the emission of gravitational waves. And by substantial, I mean in some cases up to thousands of kilometers per second. I think the maximum you can get from an astrophysically reasonable system is about 5,000 kilometers per second. The escape speed for most of these clusters is somewhere in this regime. So really, we expect these things to be terminated at about the third generation. So the first question we can ask is, what is the most extreme version of this that we can look at? So we looked at the largest cluster that we formed in this simulation. It was formed from this hilariously large GMC. It was formed at the edge of a superbubble immediately after a galaxy merger. Had a cloud mass of 3 × 10⁷ solar masses. It formed a 5 million solar mass star cluster, which by the way is the largest collisional star cluster that our group has ever done, and I'm fairly certain has ever been done. That was initially created at the edge of this bubble and then destroyed by dynamical friction as it spiraled into its galactic center at z of 0.2. And so we can ask the question, well, how many actual hierarchical mergers do I get from this? Right? And we used as our inspiration GW 190412, which was a single binary black hole in the LIGO data. Right? So the reason we liked this is because it had a very nice mass ratio, a nearly 3-to-1 mass ratio. So obviously you would expect a 3G black hole plus a 1G black hole. And we can compare this to the escape speed of that absolutely massive behemoth cluster that I was talking about, which starts off, unlike typical globular clusters, with an escape speed of nearly 300 kilometers a second before evolving down before its destruction to an escape speed of about 150 kilometers a second. So you potentially have the opportunity for many of these black hole mergers to be retained by the cluster as long as their recoil speeds are lower than the escape speed. And so we looked at this, we looked at the rest of the black hole population, and we found a whopping 3 of these things. So yeah, huge rate that we can put into a paper. So it is possible to produce these things, which is nice, but what it shows us is that really there is an upper limit in most of these star clusters to what you can get from black hole mergers. And if you assume that third generation is about as high as you can go, that's about 120 solar masses. So where did all these come from? So the answer to that, we want to futz with the stars themselves that actually go into these simulations. So I said earlier there's 2 ways you can change the mass gap. You can either change the stars that we use, or you can change stellar evolution. I'm not going to talk about this, but it's a very, very neat problem. It involves actually modifying nuclear reaction rates within their measured uncertainties in the laboratory. But the idea instead, if we want to change the stars, is, well, we know that mergers can occur in these star clusters. What if we just merge 2 stars together? What if I take 2 stars with a helium core mass of 15 solar masses and 20 solar masses, merge them together, and create this unique star that is inaccessible to regular isolated stellar evolution with a total mass of 220 solar masses and a helium core mass of 35 solar masses. That is low enough that it can avoid pair instability supernova, and all I need is an environment that can produce these stellar mergers. And so if we go back to these cloud collapse simulations, what they show us is what we kind of already knew from theory, which is that these clusters are assembled hierarchically, and that they very rapidly sphericalize once you have these clumps recombining, like within a couple of dynamical times. They sphericalize, but they don't necessarily go to the king profiles that we usually know and love from Binney and Tremaine to fit globular clusters to, right? Because they're not isothermal. They haven't had enough time to thermalize. And instead, if you look at young star clusters in the LMC and SMC, this goes back to some work by Elson, Freeman, and Fall in 1987, they really just seem to be power laws, like everything else in astronomy, right? They have some flat core, and then the outer regions just have these power laws that go something like this. This is also sometimes needed to explain larger globular clusters in the Milky Way. If I look at something like, for instance, 47 Tuc, it's actually very difficult to explain both the core density and the outer regions of the cluster that have not necessarily relaxed unless I start with one of these power law models. If I start with a king profile model, it's very difficult to get both the density and the velocity dispersion correct. So we had this idea of, well, these can be very high density power laws, right? So how much can I actually facilitate these stellar mergers in the early parts of these star clusters using these realistic initial conditions? So this was a project led by Kuldeep Sharma, who's a finishing PhD student in my group. And the idea was, well, we know from observations that most star clusters, most young star clusters that we've observed nearby, have this gamma power law, following this sort of density profile down here, from about 2.2 to 3.2, give or take. For those of y'all that know some of this literature better, by the way, the Elson profile you can think of almost as a generalization of the Plummer profile. When gamma is equal to 4, this recovers the standard Plummer profile that we all know and love. And so the question is, at fixed virial radii, I crank down the Elson gamma, I get a more dense central core, and how large of a stellar merger can I actually create? And so at a same fixed virial radius, I go from normal relatively flat profile to standard Plummer profile, all the way up to now I am getting collisional runaways. This is stars that have merged together, producing black holes and stars above 1,000 solar masses, right? These are bona fide IMBHs. These are not just things that LIGO is seeing. So how do I actually do that? Well, it's not just a single stellar merger, right? Because the initial massive stars in our simulations are at most 150 solar masses. What it is a collisional runaway. So we start off and prime the pump by several binary interactions between massive main sequence binaries with 100 or 200 solar masses. And then as this process goes along, I suddenly get larger radii for my collision products. I eventually evolve to be a core helium burning star. Through this long process that only takes about 5 megayears, give or take, I form what ends up being, by the time it moves on to an asymptotic giant branch star, a roughly 1,100 solar mass star, which then immediately collapses to be about 1,000 solar mass black hole. Now, you can obviously guess there is a lot of twiddles in this, especially in the hydro part of this, right? We are making some very conservative and then very liberal assumptions on how much matter you can actually retain once you have these stellar collisions, either between giants or main sequence stars. That's sort of by design. We can't really do anything else in the middle of these in-body simulations, though we are starting now to do hydro follow-up simulations. But even in the most conservative cases, we're still getting 200-300 solar mass black holes. So we are explaining that LIGO population reasonably well. And so in the last minute or so, what I want to talk on is the other thing I promised at the beginning, which is these suckers down here, the detached black hole main sequence and detached black hole giant stars that we've seen. So I go back to this population, and this plot looks very nice. We have these new systems that we need to explain. These are already easy because they're already in a globular cluster, so that doesn't require much work, though if you want to take a look, there's some really nice papers from Kyle Kremer explaining this in detail. Looking at the astrometric black holes, right? This is another plot from Kareem's paper. They're in a very unique position in terms of orbital period and mass space. They're very wide binaries. And so we really, and unlike the globular cluster systems, they're all very metal rich, right? And so we don't actually think they were formed in globular clusters. That would be totally inconsistent with what we know about these systems. But what about other star clusters? What about young open clusters? Because we know most stars actually formed in those type clusters anyway. So the problem with open clusters, right, is that their masses, if you say 1,000 or 10,000 solar masses, are below the resolution of most of the zoom-in simulations. So we can't do the same GMC to star cluster thing that we did for the Fireballs project. But we can do something a little bit simpler. We can just say, all right, I'm going to take all the star formation from this. I'm going to assume all stars form in a 1/m² power law for star cluster simulations. And I'm going to put, and so based on that, I'm going to put 10% of the star formation in this galaxy just into clusters. And I'm going to model that forward. And so we do that. The other problem is, of course, we can't use our regular Monte Carlo in-body code for this because we are no longer in the Fokker-Planck limit. So we use the direct in-body simulations that I was referencing earlier. And so in doing so, we can actually recreate some of these systems. I'm going to speed up because I'm almost at the end here. But this is a plot from a paper where we show a couple of evolutionary systems from Ugo Di Carlo, who was a postdoc in my group and is now an assistant professor at CISA in Italy. And if we look a little bit more in detail at this, what it actually turns out, if I plot the intrinsic population of black hole star systems and the detected population of black hole star systems as a function of their age, this is for the entire Milky Way-like galaxy, convolved with Gaia's detectability as best as we could model it, you can clearly see that for basically everything older than 100 megayears, the dynamical population in red here dramatically dominates it, right? That's the same is true for the detected population in dotted red down here as well. And so overall, per unit of stellar mass, star clusters, these open star clusters, are nearly 2 orders of magnitude, actually more than 2 orders of magnitude more efficient at producing these systems than isolated binary evolution. We were able to integrate both the in-body simulations and an isolated binary population to compare it to using the same assumptions for binary stellar evolution. So we made some forward predictions from this. We expected about 7 binaries in DR3. This was a post-diction, obviously, versus 2 that were found, which, you know, I'm an astronomer. I'll call that good enough. Our forward modeling predictions are that we expect anywhere from about 60 to 200 binaries to be detected in future data releases. This is black hole star binaries. And about 80% of those we expect to come from clusters. And so that's pretty much where we are in terms of this. I'm going to spend 10 seconds talking about this weird sucker that just came out, Gaia Black Hole 3, because it's in a stream. And so this very nicely connects all the stuff we were talking about yesterday to all the stuff we're talking about today. Because if I go and look at this system, this is a preprint from Balbanal et al., this 30 solar mass black hole, right, which is the mass of the things we've been seeing through LIGO, is smack dab in the middle of this ED2 stream. It has the same metallicity, it has the same kinematics, and we think it's consistent with a disrupted globular cluster, which is fantastic news for us. And so I'm going to leave with this slide right here, which shows what we're working on now. So obviously, given the tidal physics that we were able to put into these simulations, we are now working to re-inject the ejected stars from our star cluster simulations back into the fire simulations in order to resolve what the stellar streams produced by these things will look like. The eventual goal is that we're trying to make predicted catalogs, star by star predicted catalogs, in these galaxies for LSST and Rubin. This is a collaboration led by Robin Sanderson at Penn and Tizka Starkenberg at Northwestern. This particular plot, which is our first chance at injecting these individual stars with real stellar masses and stellar evolution back into the Fire Galaxy, was created by Nand Penethespal at Carnegie. All right, sorry I went a couple minutes over time, but thank you so much, and it's been fantastic to talk with all of you again.
Thank you. Questions?
So BH3, the Gaia, the latest one, is 33 solar masses, the most massive black hole, way above the previous ones. And it has a companion that is a yellow giant, which is iron abundance of minus 2.6. So does it convince you that those that were seen by LIGO, because that matches, must have been POP3 related rather than, because otherwise we would see more high metallicity, high mass black holes?
I would have actually said the opposite. I would have argued that because we have a pretty good argument that binary black holes can be formed in globular clusters, that they can explain a substantial fraction of the merger rate. In fact, you and I are on a paper claiming they can, by rate, explain all of the LIGO binary black hole merger rate. I would actually claim that because there's this overdensity in the LIGO population at about 35 solar masses, the fact that we see something in what looks like the detritus of a globular cluster kind of ties both of those together, right? That we see this dead globular cluster with the right metallicity forming this 30 solar mass black hole. To my mind, that actually makes it stronger the case that these are coming from globular clusters in the LIGO data. Obviously, I'm a little bit biased, but I think this is a pretty good argument to make.
Thanks, very nice. Could you talk about what is the best cluster mass to make the binaries in the range where Gaia is detecting them? And then relatedly, what do you expect the period distribution as we get sensitive to longer periods to be?
So I think the ages the answer to your first question I might have as an additional slide. No, I take it back. So in terms of the masses, the more massive it is, the better. And we actually showed this in the paper that if you plot the contribution from individual star cluster masses, according to star cluster mass, and you convolve that with that 1 over m squared assumed cluster initial mass function, it's about flat. It's actually about uniform. So you can say that roughly speaking, the more massive clusters are about m squared more efficient at producing these detached black hole main sequence stars. Now, you asked about the period distribution. We have that in our paper, and it can get a little bit wider for the clusters that are pulled apart, but I don't remember the exact bounds off the top of my head, I'm afraid.
Okay, thanks. Let's thank him once more and move on to Elena.